So let's look at this problem. It's one of the series that we've been working on, finding the internal shear force and bending moment as a function of x. So what we like to do when we get started is imagine the structure cut there, and then looking at whether you want to work the left side or the right side. And I don't really see much advantage in either, except if you did work the right-hand side, all your dimensions would be what? In terms of what? What is the length of that? It would be 18 minus x. So that just makes it a little clumsier to deal with. So I think the left-hand side is the one I want to work on. We could do the right-hand side and we would get the same result. Now with that in mind, then really all I need are the reactions at A. I don't really care too much about the reaction at B. So I'll assume at A, I have a shear force at A acting up. It's a pin, so I don't have any moment, and this is a beam, we're not going to worry about axial load. So I just have one unknown to find there. So I'll probably sum moments about B to find my reaction or my shear at A. I'm going to have to deal with this distributed load. Since I don't remember the area of a trapezoid and its centroid off the top of my head, I'm going to divide it into two groups. The first one will be just the rectangular piece, which has a height of 1 and a base of 18, so that would give me a force of 18 kips. And then my second force would be the triangular section. What's the height of this triangle right here? It's not 3, it's 2. So it would be 1/2 base 18 times height 2 gives me, oddly enough, another 18 kip force. So I'm going to sum moments about B, and I'm going to use, again, right-hand rule for my sign convention. Make sure everything's in equilibrium. So both these forces about B are creating what kind of moment? Positive or negative?
About B.
Positive. So the first force, 18 kips for the triangle, what's its moment arm? What's the distance from B to its centroid? That should be 1/3 the distance. 1/3 of 18 is 6. Then I get over to the other 18 kip force. Its moment arm is half the distance. Half of 18 is 9. And then I get over to my shear. What kind of moment does it create about B? Positive or negative? Negative. And it has a moment arm of 18. So I'm thinking the answer is 15. Is it 15? Yeah. All right, good thinking. 15 kips. And it came out positive, so I have positive shear. So when I write my equation, when x is equal to 0, I better get a shear of 15. If I want to check my equation for the shear at the other side at B, it might not be bad to have that in your as a resource. Let's go ahead and sum forces here and get my reaction at B. Now to do that, I'm going to go up and assume positive shear at B. Positive shear at B is up or down? It's down. So when I sum forces, I'm going to have my shear at A acting up, my shear at B acting down, then I'm going to have minus 18 kips and minus 18 kips. Of course, I know my shear at B is positive 15, so what's my shear? I'm sorry, my shear at A is positive 15. So what's my shear at B? Negative 21. Is that right? Because positive shear at B is down. That's the sign convention, right? Because if I imagine my body here and I push down, which way does it rotate? That's clockwise. So positive shear always rotates the element clockwise. That's the definition. So my equation for shear ought to tell me when x is equal to 0, I ought to get positive 15, and when x is equal to 18, I ought to get negative 21. If it doesn't, then something's not right. Okay, so now the fun part starts. I'm going to come over here and draw a free body diagram. On my left edge, I know the shear at A. It's acting up, and it's 15 kips. And that's it. And I know this has a distance of x. And I'm going to go ahead and draw in the bits and pieces that I have. This is highly exaggerated just so I can have some room to work with. So there's my rectangular piece, and there's my triangular piece. What's the height of the rectangular piece? 1 kip per foot. And you'll notice it's a constant, so that's an easy equation to write. So what would be then this concentrated equivalent force? I'll call it force 1. What would be force 1? It would just be 1 times x, so it's just x. Right? What would be my triangular force? I'll call it F2. Well, I know it's a triangle, so it's 1/2 base times height. My base is x. What's my height? Well, I know this little bit is 1. So what's that piece? What's the equation of that line? Well, first of all, what's the slope? Rise over run. It looks like it changes 2 over a length of 18, so that's a slope of 1 over 9. But it doesn't start at 0, it starts at 1. So this should have an equation of 1 plus x over 9. And we can check it. When x is 0, I get 1. That's right, 1. When x is 18, I get 3. It matches. So if this whole height is 1 plus x over 9, and this piece is 1, what's this piece? X over 9. You add them together. 1 plus x over 9 gives me the equation. See that? Well, it got really quiet. You guys are staring at the screen hard. It's a good time to ask a question. I think. No? It's not a good time? Is the fog clearing? Maybe you weren't foggy at all. I know I was this morning. I may still be. I woke up this morning, I was walking through the house, I thought there was somebody in the house. My wife had left a hat hanging on an inside window, and I saw the hat and thought it was somebody's head. It scared the crap out of me. Then the dog started barking. It was a big mess. But nothing a cup of coffee couldn't cure. Mr. Andrews, your gallon jug is starting to be quite adorned.
Yeah.
You don't have any little stick-on flashers or blinking lights or anything? I think you should develop some kind of gauge that tells you how much you've inhaled or not inhaled. You should plot that and integrate it and see what you get. I think an Excel graph of your intake would be interesting, don't you think? I think for homework I'll assign that. Oh, and you have a drink on cue. Very nice. All right. While I've been waiting, have you guys seen it yet? Does it make sense now? So now we just proceed. So, what is the force F2? It's 1/2 base x times height x over 9, which is what? X squared over 18. The distance, I'll call it D1 from the cut to force 1 is what? Well, it's a rectangle, should be halfway. The base is x, so that should be x over 2. And the distance from the cut to force F2, which I'll call D2, is what? Triangle is always 1/3 from the big end, right? So 1/3 of the length is x over 3. So in these problems, this is the challenge. If you can build the free body diagram, then the rest is just apply your equilibrium equations. Did you have a question, Mr. Sanchez?
No.
Oh, you're stretching?
I mean, it's still the same thing we've always done. It's just you have to write in terms of x because you can't calculate.
So now when you ask Dr. Palazzolo about something, and he always just says some of the forces equal 0, some of the moments equal 0, right? He always says that. This is why. Because that's what we do. We sum forces, make sure they're equilibrium with some moments. It's just, it's the thing that we're making sure is in equilibrium is the trick. Making sure that you've defined all the terms correctly and accounted for all the forces. So let's go back and add on that face that this is positive shear and this is positive bending moment. Things that we're looking for. Once we have that, we'll just dive in. So, assuming right-hand rule, I'm going to sum moments at that cut distance and make sure I have equilibrium. That moment with my convention is positive. Force F1 and force F2 about the cut are positive or negative? Positive. So I've got F1, which is x, times its moment arm, D1, which is x over 2, plus force 2, which is x squared over 18, times its moment arm, x over 3. And then what do I need to account for? The reaction here. And that 15 kip creates positive or negative moment about the cut? Negative. So that'd be minus 15, and its moment arm is x. So solve for the moment. I'll try to write these in their highest order first. So this is x cubed over 54. So I'll start off with that one. Minus x cubed over 54. And this is x squared over 2. And that is 15. So there's my moment equation. I should have units of kip feet. Does it work? Where do I know the moment in my structure? Yeah, what's the moment at A? A pin. Should be 0. So is the moment at x equals 0 actually equal to 0? When you plug in x equals 0, you get 0. Where else do you know it to be 0? B. So if I plug in a value of x equal 18, is it also equal to 0? That may take a minute for you to check. It's like sending a text message. Do it quick. Just all thumbs. You know, if I'd have seen someone working their calculator with both hands and just their thumbs back in the day, I would have thought that you were from another planet. But now it's thank you. But now it's very common, right? You guys can type faster with your thumbs than you can all of the 10 digits combined. How else would I do what? Yeah, like everybody, other normal human with 5 fingers.
That's awesome. How is that? How are they even asking?
You want to have a race? All right, so that's good. So far, so good. So now the next step will be to find out if it matches the differential relationship. So if we sum forces in the y direction, what do we get? Well, this shear force is down. F1 and F2 are down, so F1 was minus X, F2 was minus X squared over 18, and then the reaction 15 was up. So if I solve for the shear force, again I'll write them in order. Looks like I get minus X squared over 18 minus X plus 15. And that should be in units of kips. Now we got a lot of things we can check here to see if we're good. Quickly, is the derivative of the moment equal to the shear? It looks like it is. We also know the shear someplace. We know that the shear at x equals 0 is what? We solved for it. 15. If I put in x equals 0, do I get 15? Yes. And also I know that the shear at x equal 18 should be equal to minus 21 kips. If you put in x equal 18, you get minus 21. Mr. Barnes is quickly thumbing it in. Answer is?
I'm still doing the
moment at 18. Anybody else get it?
Yeah.
Yes? Excellent. I had a feeling it would. Every other indication that we were going right. Now, a different question. Where is the maximum moment? I have an equation for moment. Where is it the maximum value? You could plot it and look at it. What else do you know about maximizing or minimizing a function? What happens when a function is max? What's the slope at a max value? 0. Do we have an equation for the derivative of the moment? Yeah, it's called the shear. So if I can find where the shear is 0, that will tell me where the moment is maximum. Can you solve that equation and find what shear is 0? I think you could do that. That's just a quadratic equation. I'm not going to do it now. And I wouldn't expect you to do it on the exam, but I would expect you to be able to pull it off on homework. So you could find where this value is 0, and then once you know that value where the shear is 0, you plug it in here and you find the maximum moment. So in this case, it's where the shear equals 0 will tell you the value of the max moment. So that's pretty handy. So we're going to use that as we move forward, not today, but on Thursday. Knowing that the shear is 0 is an indication that you have a maximum or minimum moment. So if you're drawing a graph of the shear equation and it crosses the axis and has a 0 value, then you know where the moment's going to be max or min. That's pretty handy. Now, let me go ahead and stop this and we'll talk a little bit more. Any other questions about this one? This one took 18 minutes with all the stuff about water and everything else in there.